Good morning, everyone. Welcome to the Warren Lecture. I'm very happy to have Lili do here. I'm not sure how long, I think I met you when I was a grad student, so
Right,
it's
a long
been
time
like
ago.
8, 9 years or something
Yeah.
that I've known her. Lili is now at the University of Florida, full professor. She works on network modeling, operations research, really applied to automated electric vehicles, and I think we're going to see some of that today. But she's also been recognized. She at the Transportation Research Board Network Modeling Committee. She was the founding member and the chair of the subcommittee on emerging technologies for network modeling. So she's been working in this area for quite a lot. She's also extremely good at getting NSF funding. Very impressive. She's on the editorial board of Transportation Research Part B, which is one of the top journals in transportation. So overall, very impressive record, and I'm really glad that Lee was able to come here to speak to us. Thank you.
Thank you. Thank you, Michael's very good introduction. As he mentioned, we actually know each other a long time ago, and Michael helped me a lot in the subcommittee emerging technology in network modeling. And he actually did a very great job in his area in research. He's also very active in network modeling committee. I think right now I send a lot of papers for Michael to help me on review for Part B. So it's the first time, I got a chance to come here and to talk about my research. It's really my great pleasure. And for today, I would be very happy to share my not just one research paper. It's a big track of research regarding robust and equilibrium CAV coordinated in vitro routing, leverage game theory, machine learning, and distributed optimization. Before I move to the details of the presentation, I want to give a quick survey. So how many of you use Google to find the route before your trip? See, I almost say everyone. So this research is quite related to this application. So, we all use GPS or some other mobile apps such as Waze and Google Maps to find the route before we start a trip or on the trip. Some GPS even can keep on changing your route according to the real-time traffic. So, but my question is this kind of mobile app really help us in transportation from a system point of view? And this is the question I want to ask. And actually, there are a lot of study already do the survey, or they collect the trajectory data, they collect the traffic data. They recognize that this kind of Google Map or Waze or some other route suggestion apps, they actually do we call it independent routing mechanism. Basically, everybody checks the app, get the real-time information, and they give you the best route. You take the best route. Usually, it's the minimum travel time, right? And this kind of independent routing mechanism, and if all of us, for example, right now going from Minnesota University start to airport, we will very likely get the same route, right? Then we are going to run into that route. And of course, there's some candidate route, but nobody going to take it because Google tells us that that is the shortest path, right? So this happened very common. We all run into that shortest path, and then got that one congested, and very possible later Google recognized, because they have the sensor, they recognize this congestion, and then they start to suggest another route. So this process actually will, oscillate between candidate route in the network, and it's actually cause more traffic congestion and what's the traffic condition. So this is not something I create, and there are some research papers they already recognize this based on the field data. So, and then we think that independent routing mechanism actually give very high priority to user, to traveler, to yourself, because everybody is self, right? It's selfish. You want to find your best route. You don't care what happened to other people, right? So, and very naturally, we can think about another kind of routing guidance that we call the system optimal routing. Basically, if we have a God on the head, and then this person or this agency can assign route choice for everybody to make the whole system perform best. This is we call the system optimal routing. But unfortunately, nobody going to use this one because the system routing definitely will sacrifice somebody's interest, right? So, and the plus is a huge computation problem. Think about, 1,000, 10,000 people driving on the road, or start a trip, and you need to assign route to everybody. It's super difficult. So that is the system optimal route is not work. So, and right now, and also very important is about compliance and equity, because the system optimal route will sacrifice somebody. Then you need to ask who should satisfy, you or me. So nobody wants, right? So this is some problem for system optimal route. And in our study, we want to develop another, method we call the coordinated routing or mechanism. For this one, we want to balance system performance and also user optimality. And at the same time, we try to come out to some mechanism design so that we can address the compliance and equity issues. So I will move to detail to talk about it. So this coordinated routing consider some key components as shown in this picture. Basically, we need to have a group user, they are willing to sharing their route choice preference or something like that. And we also need to have information center to collect the traffic data, to collect this kind of opinion. And then we set up our, we set up our correlated routing, I call the CRM, by this following step. First, number one, each route has some predefined candidate route based on the general or historical traffic information. You can have 3 or 4 candidate route you think you have most interest. And then each vehicle will iteratively update your tentative route choice. You just say, for example, in this picture, the right vehicle have 2 candidate route. He can just propose, say, hey, based on current traffic condition, I want to take route 1. And the other is the green vehicle, maybe think I will take route 2, just based on my knowledge of current traffic information. And then this kind of idea will send it to information center. Information center will collect this information, aggregate it, and do the traffic prediction and send it back. And when the red and the green vehicle gets a new idea about traffic in the future, they may change their mind based on their own interest. And we want to this process go iteratively until they converge to an equilibrium joint routing decision. This is what we mentioned about CRM. And in the entire trip, you can keep on doing this. And basically, you can update your route choice according to the real-time traffic information until you reach to your destination. Okay. So this is the idea of coordinated routing. I use this example to explain it in more easy way to understand. Here we have green and red vehicles, and each one have 2 candidate routes. And in this example, I think I set up the route choice as a preference basically. And for red vehicle right now, I have these 2 routes looks even, and I just give half to half kind of preference. And for the green vehicles, and I gave the 0.3 to 0.7 preference. Basically, I prefer the other one 0.7 more than the one goes to the top, and then make a turn goes to downside. So, and this is our initial set, and then we send this information to the information center, basically route priority, and the information center is going to get this information combined with background traffic, and then send back the traffic condition prediction. And the green and the red vehicle receiving the new information, and I very likely will change my idea if I notice that the route I prefer more actually will get very much congestion in the future. Maybe I want to switch to another route. This is a very natural response from user side. And we want to have this keep on going until we reach to some point and we all satisfied. We don't want to change anymore. Okay. So this is in mathematics, they call it equilibrium, so decision equilibrium. Just nobody want to change their idea, their decision anymore. So sounds not very complicated, but if we want to make this method work efficiently and rigorously, and we need to deal with some mathematical difficult. Number one is how we're going to model this kind of game theory or this kind of negotiation process. Number two is if we have, you can see this kind of routing decision involve many vehicles in real time. So how are we going to solve it in real time? You know, you don't want to wait half hour to get a choice about your route. Usually you want to get the decision in a few seconds. So, and also, you know, how can we make sure user gets the route they are interested, and how can we make sure if we follow this kind of routing guidance, we're going to make the system better. So this is what we call the optimality. And another question is, as I said, this kind of CRM involves many vehicles, individual decision in real time. And then for a big city, such as in Minneapolis, there are many vehicles and need to make a decision in real time. And how can we deal with this scalability problem? So, you know, our research want to solve all this research question and challenge mathematically and theoretically. So, and I want to use this slides to show the methodology map. And you know, to solve all those challenges, there's no way we can do it in one paper. So it's turned out, you know, around, I think so far we got almost 12 or 13 papers on this topic. So I want to start with beginning. About modeling, we can do you know, mixed strategy game or pure strategy game. For mixed strategy game, that means the CRM will only give you the routing guidance preference. Just like I only tell you that you only end with the preference, such as I prefer this route 90%, the other route 10%. But the user does not propose, I'm going to take this route for sure. This is not the information considered in you know, mixed strategy game. And for this kind, if we model the CRM by this mixed strategy game, and we developed the coordinated routing, and we actually also extended this study to parking problem, because parking actually have very similar situation. And the other way to model it is the pure strategy, just as every time user only propose, say, I'm going to take route 1, or I'm going to take route 2. I very confirm, you know, which route I'm going to take, not the probability, okay? So if you model this kind of negotiation by pure strategy game, and it came out of some other CRM modeling and the solution approach. We already finished the study for CRM, use pure strategy, and also extend this method to ride sharing. And because in ride sharing, you also need to determine which Uber car you're going to take. And there are many users need to make a decision at the same time. How can we coordinate their decision? So this is, you know, for pure strategy. And then this is, you know, our first set of study just to focus on the algorithm and also focus on the modeling part. And this is our seed work, and has been published. All this published four papers to demonstrate the methodology. And the next time we want to involve machine learning. Why? Because we haven't solved the scalability problem. So with this one, we start to design some research. We named it as the cluster-based mixed strategy or cluster-based pure strategy. Basically, I will talk about this idea very soon in the presentation later. It's just that we want to separate a large scale of traveler into different groups, but we are not going to do it straightforward. We will, you know, strategically separate them into two different groups and then do CRM independently without hurt the system performance very much. So I'm going to mention it very soon. With this idea, and we also want to, I also want to mention that for this CRM, basically you probably already noticed that it is an equilibrium solution. Basically, it's come from game is equilibrium solution. Equilibrium solution will never guarantee system performance because it still give high priority to each individual user's decision. When I mean system, I mean the overall performance, okay? So, and to address this challenge, we involve another idea we call the information perturbation strategy. And more exactly, we will develop some information perturbation strategy to push the equilibrium solution of CRM to some kind of equilibrium solution is closer to the system optimal, but not exactly system optimal. And I will talk about this idea in the presentation also. And the last is by combining all this idea and basically we want to integrate cluster information perturbation with different game theory model and to see the effect. And another one I want to mention is to push this solution of CRM to someone closer to system optimal. Beyond the system information perturbation build upon mixed strategy, we also develop another research use correlated game. And this is the last topic I'm going to mention today. So this is the map of our methodology. We're actually still developing, because in this map, we haven't involved tri-float dynamics. And we are developing another track of study, try to integrate tri-float dynamics into the CRM. So for today, I will mainly focus on this part, this one with the red color, because I'm not able to go over everything. And my purpose is I want to share idea and thought with you. So for all the study, I'm not going to detail mathematical proof or this kind of stuff. If you're interested, you can read our research paper. I want to mention that for the mixed strategy part, we usually developed the simultaneous updating distributed algorithm, and for the pure strategy, usually we developed a sequential updated distributed algorithm. Why? Because for this group of study, if you develop a simultaneous updated distributed algorithm, we can prove the convergence. But for this side, if you develop the simultaneous updated distributed algorithm, I cannot prove it. I prove it, and when I do the mathematical study, I cannot ensure the convergence. So I will compromise, make it become sequential update. It is not very efficient in times wise if you compare to simultaneous update. So this is the the big map of our methodology development. And yeah, let's go to more details about this side. So number one, I want to quickly go through how we developed this kind of mixed strategy game, integrating role choice behavior. Again, for this game, we involve M players, and they are willing to sharing the tentative. Basically, they are willing to join the CRM, to sharing ID, sharing tentative role choice, and also updated role choice timely. And so this. These M players, vehicles, you should have a fixed number of candidates routes, and then they will every time propose their route choice priority, and then according to the latest traffic information, and also the decision from other users. How they determine their priority? We use the multinomial logic choice model. This is well accepted in transportation, so I won't spend much time on that. And then the equilibrium condition is expressed by this one. Basically, we after we go through this CRM, we want to reach out the equilibrium preference that nobody want to change your preference anymore, just as what I shown in that example. So, and this is the framework of the game. For this game, and we can prove that it have an equivalent mathematical program. And why we want to find this equivalent mathematical program? Because this program is optimization, have good feature to develop the solution algorithm. Once you find this equivalent optimization problem, you can use a lot of optimization algorithm to solve it. So, and to do the proof, we write the KKT condition of this mathematical program, and we can show that this KKT condition is equivalent to the equilibrium condition I give for game. So that is the proof. And another good thing is we notice that this mathematical program have unique solution. Basically, they have convex objective function and convex constant, so we can make sure they have unique solution. And then on the other hand, we know that game have unique equilibrium. That's good, because that means if we convert algorithm converge, we always convert to the best solution we want. So, and then we developed a distributed algorithm. When I say distributed algorithm, that means each vehicle will take independent calculation load and then send to information center to synchronize and then send back. We do this iteratively, and so that we can make the solution, the computation converge to the optimal solution we want. And each vehicle only take very simple updates as shown in this linear function. You use your current preference plus step size and the direction, you got a new preference. The direction is the difference between your priority coming from the logical model minus your previous priority. Okay, the trick is the step size. If you do not cite the step size smartly, the algorithm won't converge. So you have to carefully select the step size. So this, why we developed this paper involve a lot of math. Actually, majority of the mathematical work of this paper is we try to prove and try to find a mathematical bound for this step size, so that if you satisfy this bound and your step size satisfy this bound, and this algorithm, this distributed algorithm will always converge to the equilibrium point you want. So if you're interested about this distributed algorithm design, I would recommend you to read this paper. Okay, for today, I'm not going to that much detail. Not many details. And we tested this CRM on a small network in the Sioux Falls network. It's just so well known in transportation. And, I just want to mention here, we use the BPR function. And that is one point I mentioned at the beginning. In the presentation of today, all our travel time is estimated by BPR function. Transportation people will definitely criticize this is not perfect for real-time decision. But this is all what we can do, considering the complexity of the problem 5 years ago with our technology capability. Just recently in this year, we started another research to, we give up this BPR function instead to use, dynamic travel time prediction. Basically involve traffic flow dynamics model in our CRM. That work is actually was just done in the summer. So it's going to be presented in TRB. But for today, I didn't involve it. Okay. And so we do these experiments, then we notice that as more and more people start to use this CRM, the system benefit actually become more and more significant. So this actually makes sense to us. And this slide shows the average user benefit. This figure shows the system benefit. And basically, we use the 6th trump time of the coming from the IRM divided by the system trump time come from the CRM. Okay, so then we can, this research just to confirm the CRM can, benefit the system performance because each user still make decision based on their own interests. So we didn't push user to sacrifice, but the result shows that, as I said, this is a equilibrium solution from game. And because of the price of anarchy, we can never guarantee what level of system performance we will reach. So this is the weakness of the initial CRM study we developed. So from here, to solve this kind of automatic problem, we start to develop information perturbation strategy. Okay. Before I move to the information perturbation strategy, I want to just use one slide to talk about the scalability issues because one term here will be used in the information perturbation. So this research tried to develop the CRM built upon the coordination groups. And then these coordination groups is classified based on a term we developed. It's called coordination potential. This coordination potential actually try to quantify the route computation between users, between travelers over the entire network. It sounds very abstract, but actually we are doing it all the time. Well, every time when you pick that route, you contribute to the congestion on that route, right? Other people saw the congestion, they run away. So I use this example to show this concept easily. Just we give an extreme case. All the routes only have capacity 1. Basically, each route can only take 1 vehicle. Okay, this is extreme case. Then you can see for the purple vehicle have 2 candidate routes, and the orange also have 2 candidate routes. Same thing for the blue, but their route have some overlap, right? And if the purple decide to take this route, it's actually push the orange vehicle goes to another route. The behavior of the orange vehicle or the route of the orange vehicle actually push the blue vehicle to go another alternative route, right? So these things actually happen in transportation implicitly every time, when we do the route charts. Just we didn't have a quantitative way to measure it, or we didn't give enough attention to this kind of computation. I call it the loose computation. Okay. And in our study, we actually try to quantify this kind of computation. And we developed some very complicated mathematical model to quantify the direct route computation. Basically, the orange and the purple, they have the route overlap. So they too actually compete directly, okay? And we also developed very complicated mathematical model to quantify the computation between the blue vehicle and the purple vehicle. If you originally just say their route, they are not overlap. Since their route is not related to each other. There's no competition between them, but they both share some route with the with the orange vehicle. So they indirectly compete the resource on the network. So we again develop some, mathematical model to quantify this indirect computation between vehicles on the road. So this just a simple example to show idea, but think about on the network, you have 10,000 of the vehicles, each have 3 or 4 different routes. Things will become very complicated. But once we can quantify this kind of direct and indirect computation, and I also calculate, if you want to find the coordination group, we call it the coordination potential. But if you think about the route computation, you can also name it as a route computation index. So this two names both actually means same thing. And then later we will use the computation index. So after we can quantify this, and then we start to build a potential, and we call it the computation potential graph, basically over all the vehicles subscribe for this CRM app, and we are going to build this kind of potential graph. For this potential graph, based on this kind of direct and indirect computation index, basically this is the weight of the link. Each node, it is a vehicle, okay? Then we can use the community learning or some machine learning method to classify it into different groups. And when we do this classification, we hope each individual group will have the feature that vehicle within this group have a high computation index, high potential to coordinate, and vehicles between in different group have very weak computation potential. You just think that if you are in the south side of the city and you travel in the south side, and the other people travel in the north side of the city, they travel in the, these two should separate into different groups because they are not completely not very related. So it might be better separate them into different groups. That is what we do here. Just simple conceptually you can understand this way, but mathematically is you have to build on some graph, use some graph theory, and also machine learning. More particularly, we actually develop some adaptive clustering algorithm so that we can end with this group perfectly based on what we interest, such as we want to find the number of the group exactly at some point that the system performance, because when you separate all of them into different groups, you definitely will sacrifice the system performance, right? Because no matter how weak the competition between different groups, you still have some manual computation. If you ignore them and do the coordination routing independently, you sacrifice system a little bit. But if you separate this kind of group smartly, you can minimize that system performance compromise. At the same time, you keep the merit of CRM. So then the trick is how many groups we need and who should be in which group. So that is our paper, this is our paper shows that traditional clustering algorithm cannot satisfy this requirement. So we developed our own clustering algorithm. We use it, we call it adaptive clustering algorithm. So for the technical detail, I would like to recommend you to read this paper. And this approach, actually this computation index and also coordination potential actually can also be used to EV routing problem or some ride sharing problem. We have some related paper developed in recent years. Okay. Next, let's go back to information perturbation. So this flowchart actually shows how we do the coordinated routing. Basically, each user get information, will evaluate the traffic, propose your route choice, and then evaluate if we came to equilibrium or not. If not, we go back, send information to information center, then information center give information to user doing this procedure again. So I want to say in this procedure, and we guarantee user optionality because each user still make your best choice, right? And in this step, it is information send information to users. And in this step, we think we can mix in the idea of system or the interest of system. Basically, we want to use the strategic information perturbation to affect users' route choice decision here so that we can make this equilibrium close to the system optimal. Okay, how are we going to do it? This is how we do the information perturbation. If you are coming from transportation, you will say that, this is the convex combination between two travel time. This is the marginal link travel cost. This is the average link travel time. So we do the convex combination so that we got the information perturbed travel time. Why we use this marginal link travel cost? Because if you use the marginal link travel cost to, if everybody follow this kind of marginal link travel cost, the equilibrium solution will go to system optimal. This has taught in transportation class. I believe Michael taught that. And if you use the average link travel time, you go to the normal equilibrium solution. So, but if we got the convex combination, we got some solution in between system optimal and the original user equilibrium. So this is the root of the set, okay? And then, the difficulty is how can you guarantee this works? And how can you guarantee how good this works and how much we can perturb? So that's the research questions. I want to show it here. So mathematically, this is how we describe the information perturbation if we use the CRM. So this mathematical model is exactly the same as the MP CRM for CRM I presented at the very beginning. The only difference is we change here to the perturbed information. And then you can see that for this CRM, if we use the average or the original travel time, you're going to get the normal traffic flow. But if you use perturbed information, you're going to get the perturbed flow. Okay, and put together, we can get a difference of this objective function we call the equilibrium cost. So this is the one index we got. And at this point, you probably don't know why we need this difference, but following you will know that. And similarly, corresponding to this, equivalent mathematical program for this kind of coordinated routing, we can also have the system optimal formulation. Basically, we describe how we get the system optimal, how we measure the system performance if we use this perturbed information to send to users. And this is, and users still make a choice just every time, just propose their preference. So this is the system optimal, and we borrow the formulation published by Dr. Yang in 1999. Okay, and this is also well known in transportation. So if we do this, then for system optimal, we can also get a difference. Let's choose the system gain. Basically, you got a system optimal under the normal travel time information and the perturbed information, and you got this difference. And corresponding to this system optimal, we can get the user optimal. Basically, for each user, you can also make your best decision according to the information, perturbed or not perturbed. Okay, so then you can get the user loss. So now we have three items, three data. Okay, it's equilibrium loss, equilibrium cost, the system gain, and the user loss. And now, we did mathematical analysis, and so that we can guarantee that if we do the information perturbation, no matter how much we perturb, we always get the system gain greater than the equilibrium loss multiplied this parameter. Okay, we also do the mathematical proof to show that most of the time the user loss will less than this equilibrium cost. Why I say most of the time? Because the mathematical proof actually give more complicated description to condition that when this is going to happen. For the presentation, I just cannot put everything here, so I just give a rough idea here, okay? And put these two solutions together, and we got very interesting insight. Then you will notice that if we give a small perturbation, just 0.1, you're going to get the system gain will be 9 times the equilibrium loss. And at the same time, the user loss will less than the equilibrium cost. Okay, so it gives us some hint that small perturbation is preferred. But still, we have no idea how small is good enough or what's the best perturbation we want set up. So with this question, we develop another study based on the experiment result we got here. And if we plot the system gain along different perturbation level under different traffic conditions, this is just to show one of them, okay? Then you will say this is the curve of system gain. And this is the curve for average user loss, okay? And this is the curve for the worst user loss. You're the bad boy, you always get the largest user loss. Okay, so this is the worst case. And then we notice that there is a perturbation here. We got the big gap. Basically, we got the best, the maximum user gain, system gain, and the relatively small user loss. And also, to ensure the compliance, we want to have a bar, basically limit the worst case. Yeah. If we give these two conditions, we actually limited the perturbation within a certain kind of range. Okay. Then this is how we observed from experiments, but just based on the experiment, you still cannot rigorously tell people how you're going to set up your perturbation. So then we developed another study, and then we start to bring in machine learning. Okay, here we start to use the data-driven approach. Based on what I described in that figure, you can easily say, if you can set up an optimization model like that, this is the average user loss, this is the system gain. You want to minimize this gap, right? And also the perturbation will be between 0 and 1, and you want to have the worst case bounded in some threshold. Okay, this is the very natural optimization idea. But the difficulty is we don't have the formulation for all this data. Because if you go back to the mathematical model of MP, you will see that it's very difficult to get analytical formulation to describe all these three items. That is why we go data-driven approach, and we want to sample. When we go to data-driven approach, we still have difficulty because we don't have a system to set up this CRM, no matter in field or by simulation. Because there isn't any simulator can set, right now have this kind of routing guidance, and we create it by ourselves. So then, what we do is we will use the MP. I showed, at the beginning, MP integrate the information perturbation as the simulator. We call it the mathematical simulator, or in literature, some people also call this simulator as the computer simulator. Okay. And then we use this as a simulator, and we sample the data using sample and some data science approach, and we try to build the formulation for these three data. Okay, and then after we solve the formulation of the three data, we can put into the optimization, then we can get the best information perturbation. But since it's not trivial, because, for example, this is a mathematical model, and our input data is the OD demand, is the candidate route, network topology, and the perturbation level. So think about the network topology. How can you make it become a data machine learning can understand? That's hard, right? Because you don't have a very clear index so that you can clearly describe the information, the topology of the network, the number of nodes, the number of links, how nodes and links connect together. It's just so hard. And another thing is, if you only have the network topology, it's still not enough. We want to describe how strongly people compete to each other for the route. For that one, there isn't any straightforward data we can use. Okay, so if you want to develop this kind of data-driven approach, the immediate difficulty is how you select your features. This feature is not naturally exist in reality. We have to create it by ourselves. So in our study here, we start to use this computation index. Remember, when we do the clustering, when we do the solve the scalability problem, we introduce the index, we call it the computation index. And we think this computation index describes the network topology and the distribution of OD very well. And we call it concentration in our study in this information perturbation. And we use this feature to the mathematical model so that we can, we can generate all the data, and then we use Gaussian regression to build all this formulation. So this is the big idea of our machine learning aided approach to find the best information perturbation. And I don't have much time, but I want to quickly go through. Even you have the feature selected, it still have difficulty to do the sample because this computation index is very abstract and complicated, and the mathematical formulation is very complicated. If you want to measure the computation index, you need to sample the OD, you need to sample the demand distribution over the network. If you do it randomly without any control, this is what you get. for each demand, you always get one concentration. You not get enough diverse for the data. So that is the difficulty we met. And then we recognize for this index, if we want to get enough coverage of the concentration under a single demand, when they distribute different over the network, we need to come out some sampling strategy by ourselves. Okay, we need to design this sample. So what we do is we use community learning to separate the network into different community. And within each community, we use federal design to determine what's the percent of flow will go within the community, what's the percent of flow will go between the community. So that, and we do this for all these 4 zones for this network. And then we pick the combination that satisfy, they plus together equal to the total flow, basically equal to 1. And then we do the sample again. This is what we get. Then you can say, for each demand, you can say there are many diverse concentration. Okay, this is how we solve the sampling problem for the concentration. For OD demand, you can easily say sample is from, for example, 1,000 to 5,000 with stop size 50 or something like that. For, but for concentration, we have scheme out this kind of designed sampling approach. Based on that, we can develop our Gaussian regression model, basically learn the 3 delta value. And when we do the learn, and we made a new question is, what we should learn? Shall we learn this delta and system gain and user loss separately, or shall we learn this gap? They will perform different, And same thing, and how to learn? Shall we learn all these 3 delta individually, or shall we learn them use the multi-response regression? So they also came out to different solution. So with all this kind of choice, we develop different optimization model. Because before we test the performance of this different way, we have no idea which one will perform best. Okay, so we just try all of them, and then we, evaluate which one perform better. So this is the result, and you can see that. And we compare our Gaussian regression solution, basically find the best information perturbation from the formulation get from Gaussian person regression. And we can also find the best perturbation with the same condition of traffic and congestion based on simulation. It's a lot of work. Okay, you need to try a lot. And then you can get the best simulation perturbation value. And then we evaluate the solution from GPR, and also with the error tolerance 5% or 10% of the simulation optimal. And they will notice that most of the model will give you the solution. For example, if you set the tolerance range is 5%, you will see that most of the model will give you 65% level of, basically 55% of the solution got from the GPR will be within the 5% of the simulation optimal solution. Okay, if you make it tolerance a bit larger, for example, 10%, you will notice that 17% of the solution got from the regression will follow in the tolerance of the simulation optimal solution. Okay, so the performance is relatively good. And most important, we find this one actually even better. You can say it's almost reached to 85%. So, and this is the first solution we got for perturbation. Another interesting solution for perturbation is we sample we test the information perturbation and the different computation level and the different demand level, and with different weight about the variance we care about the the solution from the Gaussian regression. And we notice that usually, when the computation level is low, demand is low, we want to, low level perturbation. But when the computation level and the demand is high, we will push to the high information perturbation. But if you take a look at the worst case, it just gives you some bar. Okay, we notice that the right side, right up corner actually is the area you don't want to recommend information perturbation. Basically, under that kind of condition, no matter what you do, you can do perturbation, improve system performance, but you're going to hurt some user very much. So this is not the area we supposed to, we recommend to do the information perturbation. And clearly that this information perturbation will help improve informed performance. However, it cannot solve the compliance and the equity issue very well, right? Because we can say that at some area, we should not do information perturbation, and still there are some user will, even at the optimal information perturbation, still some user will satisfy. So then we came out to some new idea. We want to develop the correlated equilibrium routing. This is a new type of game. It's different with the congestion game we developed in previous study. The idea is the information center right now is not only recommend the traffic information, they also recommend the route choice. Okay, and they recommend this route choice with the purpose to minimize system cost, at the same time ensuring travelers to be better off by following this suggestion. Sounds good. That if I give you suggestion, if you follow my suggestion, you're only better off. You're not going to feel hurt anymore. So this sounds very good, but mathematically it's very difficult. At the beginning, I first want to just quickly go through what I mean about the correlated equilibrium. This is the type of equilibrium that involve a game. Still, you have M players, and each players have a set of actions they can take. Just in your problem, such that you can take route 1, route 2. And then this strategy, all this combination of players' actions form a strategic profile site. Okay, and then this profile site actually, for correlated equilibrium represent a situation that it gives a probability distribution over all the strategy site, and so that the player has no incentive to derive from the suggested strategy. Okay, so mathematically it can be described like this way. So this is the player's utility for following the suggestion. This is the utility player I derived from the suggestion, and this is the probability determined by this correlated equilibrium. We can smartly choose this probability so that this probability is over the strategic file. Is strategy file. It's not another probability I'm going to introduce. That is why I want to emphasize this probability is assigned to this strategy profile, and this is one element. So we want to let satisfy greater than equal to 0. Basically, you can say the utility user following the suggestion will always give you always better off than the utility you are not following the suggestion. And then this probability will affect the utility calculation. Okay, so this is the standard correlated equilibrium. In our problem, the setup is a little bit different. I give this one, gray color for you to refer the previous talk. And in our study, we think each vehicle only have 2 actions. You either follow the suggestion or not follow the suggested route. So only 2 simple actions. And then we have a preferred strategy. We have a preferred strategy we call SF. And this SF is every vehicle follow the suggestion, okay, from the CERM. And that's mathematically this preferred strategy will came out this kind of probability. Only this strategy got the probability equal to 1. All other strategy 0. Okay, then the equilibrium condition can be described in this way. Okay, all the previous one 0, only this strategy will lead to this utility and greater than equal to 0. Okay, and then the question is how we measure this utility and how we design this utility. This came to our research. That is, we want to have this routing mechanism design the route preference recommendation. It is not the probability assigned to the strategy profile I discussed previously. Okay, this is the route preference recommendation. This recommendation will lead to the utility function, in our routing problem. You probably see this utility function looks very strange. Actually, this is directly come from Dr. Yang's paper in 1998. So the first part is the travel cost. The second part is the social welfare of the routing suggestion. So, and the problem, now our research is going to focus on how we determine this preference of each individual user so that we can make this inequality satisfied. And then another question is, theoretically, this correlated equilibrium is not unique. Okay, you can come out many different kind of CE and satisfy that inequality constraint. And for our problem, we want to find this CE or this preferred that preference probability that minimize the system cost. That is came out optimization model. The objective function is system cost, and then we involve the CE as the rationality constraint. Okay, and the rest of part is the basic constraint for probability. Okay, I want to particularly mention here. Here we have a little bit of variation for the originally this should greater than equal to 0. Right? Because theoretically, when you do this kind of mathematical model, theoretically, it is possible some probability equal to 0. Because probability is feasible region is from 0 to 1, right? But if you put this at 0, you will make huge difficulty to in the algorithm design and also all the convergence analysis or complexity analysis. And we change it to epsilon, we think it is satisfy reality. Because if we make this epsilon very, very small, in reality, if you tell people this probability, the probability to take this route is 0.00001, nobody's going to take it. So it came out to the same solution. So that's it, we change it to epsilon. And this gives us a lot of help, but also brings some other problem I will mention later. So this mathematical model is nonlinear, non-convex, and involve a lot of users. And rationality constraint is very complicated. It's highly coupled. When I mean highly coupled, means each constraint involves multiple users' decision, multiple vehicles' decision, not only one vehicle. This P involve everybody's decision. So everybody affect everybody. So this is what I mean coupled. So it's very difficult to get a solution online in a few seconds. Okay, so this is the difficulty we want to solve. And to solve this question, we developed a distributed augmented Lagrangian algorithm. And here I want to list my idea is we first relax this NP to NP augmented Lagrangian. And this is standard. And then to develop this algorithm, we came out with some new things such as epsilon probability simplex projection and the distributed computation load based on transformation of formulation. And also we started the robustness and the resilience. So I came out the detail a little bit. So this is on MP to transfer it to augmented formulation. I think if you have a little over background, this is not difficult. You just move that rationality constant to the objective function plus some regulation. And now this constant is the epsilon probability simplex constant. Okay. And from now on, I will change this complicated notation to X. Just make the formulation looks neat. Okay. And then this came our algorithm. After we do the transformation, we are going to solve this MPAL iteratively. At each step, we use the projected grading algorithm, grading descent algorithm. So you can see from the name, the most important element is how you do projection, how you find the grading. Okay. Then for this slide, I will talk about the projection first, because it's a relative need. So this is the simplex epsilon probability simplex constant. In literature, they actually have some well-designed algorithm to solve the probability simplex constant if you put here as 0. Okay, but because we change it to epsilon, the original algorithm does not work anymore. So we develop our own algorithm, and it came out several steps, and we have some mathematical proof to show that this algorithm will converge to the optimal solution we want. And I don't want to go to the detail about this algorithm. You can refer the detail of the papers. And after we solve the projection problem, then let's go to the grading issues. Okay, to calculate grading is related to the Lagrangian function, and this Lagrangian function. Originally, it does not look like we can do distributed computation because it's the constant just well kaput each other, okay? And then what we do is we do a transformation. For the first element, is basically system travel cost. This travel cost can be calculated by link by link, and it can also calculate vehicle by vehicle. Okay, each vehicle have the pass and each pass have the travel cost. So we transfer to vehicle by vehicle. After we do this, we notice some interesting things that the Lagrange function actually can be separated into different elements, and each element only related to one vehicle. Okay, and let's give us some good hint that we can split the traffic, the computation load to individual vehicles, and each vehicle only take the task to the grading of this element. Okay, so this save a lot of computation load and make a computation a lot of easier. Okay, and but it's the good things always give some trouble. If you do the distributed computation, you rely on the wireless communication and onboard computation very much. But what if somebody's cell phone got a malfunction at that moment, or the wireless connection is not good at that moment? So we always got a communication failure, right? So then, we need to think about the way how we're going to. We need to understand the robustness of the algorithm, and also we want to say if we can improve the convergence rate. Of course, the original augmented Lagrange method has been proved to converge to the optimal solution of NP in literature. So we don't need to worry about that. And this is the new research we want to develop. Let's talk about the robustness and the resilience. Originally, if communication is good and this grading is you can get the perfect grading to update each solution. But if you have communication loss, we are going to use the approximated grading to update the solution. And this approximated grading involves some element. This BI indicates the disconnection, and this is the weight related to the disconnection. Okay, and then we get some mathematical proof, and we can ensure that if you use this approximated grading, you can still guarantee the convergence. That means, the algorithm is robust to communication failure. And further, and we do more proof, we show that, we can still keep certain level of convergence speed even with this communication failure. This is related to the communication failure probability and also the convergence criteria you set for the optimality condition. Okay. And this shows the resilience of the algorithm. And, next, we came out with some idea is we want to improve the resilience or accelerate this algorithm's performance. And the idea is the augmented Lagrange method have each vehicle take one computation load. Basically, you calculate that the grading of this FV. And then we can prove the convergence complexity. And then we want to develop another algorithm that each vehicle will undertake a decomputation load. And for example, if you say D equals 3, then the vehicle 2 is going to undertake computation task for number F, V2, V3, and V4. Okay. And of course, we have some kind of, basically each calculation have some backup. Okay. But it's going to hurt the computation. And also we want to know if it's going to converge. And here we also do some mathematical proof to ensure it's converge. And more important, we got some insight is if we assign a large number of D, and we can have the iteration of the algorithm decrease, but for each iteration, it takes more time to compute. So then, we also, our proof also show that if D greater than this threshold, and this accelerated distributed augmented Lagrange method always recover the full gradient information. And then in reality, if you want to balance the computation load and in each iteration and also the number of iteration, we would suggest you choose the D less than the expectation of this element. Why we do the expectation? Because this S represents the number of vehicles has the malfunction in communication. This happens in a probability. It's not uncertain value. So that is why here we use probability. And with this, we finally can conclude how good this algorithm is. We first compare our distributed augmented Lagrange method with the standard SQP method, and we found that it's a sequential quadratic programming, okay? And we found that this orange, you can see, is much, much better than the existing algorithm, and it satisfies the computation requirements we set for this online application. Another thing is we want to compare this DAL and ADAL, and we noticed that, number one, they all converge reasonably good, so they both have the robustness. Number two, that we think, if you take a look at this breakpoint between the DAL and ADAL, you notice that, at some point, that before that point, the ADAL actually performs better. After that, the ADAL not, because there are too many failures. You can say if your failure probability above 94% or 95% or even higher, then the ADAL does not show good performance, but that's reasonable, right? And actually, we got conclusion that the ADAL is more reliable and a high likelihood of communication failure, but not very high, okay? And then ADAL is more reliable and preferable than large scale program, because large scale program, because for this case is 1,500 vehicle, you can say, the ADAL perform better than the DAL, when the failure probability is around 95%. So it's satisfy our expectation for this algorithm design. Next, I want to compare this correlated routing mechanism, with some other routing mechanisms such as CeRM and the previous that kind of CRM based on the mixed strategy. Okay, and we noticed that it's always performs better than CRM, and also it's for example, it's improved 55% by compared to the independent routing. But if you compare to the correlated routing using mixed strategy again, and it's improved with 3.6% of system performance. So it's still pretty good. And the more interesting, you can say this one. I like this one most because we compare for the super network, you only have 76 links, right? You can plot the link travel time or link flow, by heat map. Okay, that is why you have so many slots, basically 76. Okay, then you can see the dark color means a lot of flow. The yellow color means the light color means less flow. Then you can compare the RM, independent routing, and the system routing, and you can see that they are very different. That means system routing usually will suggest some routes people don't like to go. So this is really match our intuition, right? And the next is you can see the the CRM, the correlated routing, and the correlated routing based on the CRM and the correlated routing solution, and you can see they are pretty uniform. The color are relatively uniform on different link. This means the traffic demand was well distributed over the network. Okay, and more if you compare the correlated routing mechanism with the SOR, you see they are actually very consistent. Basically, the CRM will came out a solution closer to system optimal, but not exactly the same. Okay, and that is just what we want, because in this CRM, we still use game. Users still try to keep their own interest. You not 100% to push to the pure system optimal. Okay, so we can only make it closer to the pure system optimal. We cannot directly move to that system. Okay, so from system performance point of view, we can see that RM usually will end with the worst situation, basically the largest system travel time compared to CRM. And for CRM, usually will end with the system performance worse than the CRM with information perturbation or CERM. They both will worse than the SOR. But for information perturbation or correlated game, which one perform better? Hard to say, because the information perturbation depends on how much you perturb, right? So this is one we don't have the conclusion. So with this, it's come to the end of my presentation, and I cover 3 topics. And first, we develop correlated routing and try to solve the user's overreaction to real-time traffic information. And we develop distributed algorithm. And to solve the system performance issues, we developed the correlated routing built upon the information perturbation. And we do some mathematical proof and also data-driven approach to make this solution rigorous. And then last is we developed the correlated equilibrium routing mechanism, and we try to improve the CRM from system point of view without sacrifice users' interest. And we also demonstrate the robustness and resilience of the distributed algorithm we propose in this study. And with this, and came to the end. Thank you very much for your attention. And all this research was co-developed by my students and also my previous colleague. And this to help me in the first seed work. After that, my students further develop a lot of other, more advanced research. And this research was well funded by NSF. Basically, it's my career work. Thank you very much.
I want to give everyone the opportunity to ask some questions really. So if you have a question, I'm going to bring the mic around.
Yes, quick question. Is the framework applicable to autonomous vehicles only, or can it be applied to human vehicles too?
Yeah, good questions. So for autonomous vehicle, depends on how you implement. So if it's human drive vehicles, you can have certain kind of app is just pop out this kind of suggestion. The user will decide take or not take. And if for autonomous vehicle, the vehicle will determine take or not take. So it just depends on how you implement this algorithm. So it's applied for both type of vehicles, just how which one will make the decision. Because for human drive vehicle, eventually human determine which route going to take. For autonomous vehicle, the vehicle will determine which route going to take. Then you can set autonomous vehicle with certain kind of feature preference when they make this kind of decision. Mm-hmm.
So you showed the MP problem where you had this nonlinear, non-convex objective function and non-convex set of the feasible non-convex set. And then you also presented MPAL where you had a feasible set that was convex, but how did the objective function, did the objective function become convex for that problem? Because you showed that your algorithm guaranteed convergence for MPAL.
If I'm here correct, I want to clarify at the beginning when we developed CRM, that algorithm, that's an equivalent mathematical model we call MP. That one is convex. So but even it's convex, if you use traditional algorithm, you still not satisfy the real-time application because we want to solve a few seconds, involve a lot of vehicles. So we developed a distributed algorithm and we prove it's converged. But once we came to the CERM, and it's correlated equilibrium, this MP is changed because the objective function is system performance, it is linear, that's clear. But the rationality constraint is nonlinear, non-convex. So this makes the problem even difficult. That is why we go to the augmented Lagrangian method. Basically, we bring this defeat constraint to the objective function based on literature. This literature, we know that even we do nothing, we just solve this augmented Lagrangian function with the constraint. We can use gradient project descent algorithm, convert to the MP's optimal solution. But as I show in one slide, if you use traditional, algorithm to solve this kind of, such as the sequential quadratic programming method, the computation performance not satisfied for this online application. That is why we do a lot of work to distribute the computation load based on the model's features so that we can finish this computation in a few seconds. I think the current algorithm can solve the the problem less than 1 second with 1,500 vehicles. Each vehicle have 2 or 3 candidates routes.
Yeah, but isn't the bounded rationality constraint that you mentioned, isn't that the reason of non-convexity of the feasible set?
Yes.
So
yeah.
if you Lagrangianize that constraint into the objective function, doesn't the objective function also become a non-convex?
Yeah, but at that moment, it's not going to, you're not going to deal with that part because you're going to do the gradient descent. When you do the gradient descent, you don't consider the constant, you just keep on try to minimize your objective function. Then you do projection to the, to the constant. Once you put that rationality constant to the objective function, your constant becomes simple. It's just a linear constant. That is, how we deal with the difficult as the first step. I mean, computing this first step.
Okay,
yeah.
Thank you.
Are there other questions? Okay, thank you everyone, and thank you so much for Lili.
Thank you. Thank you.